Hello, everyone. My name is Jacoby Bussey, and I'm a TA for Econ 210. Today, I'll be going over problem set 4, question number 3, which has to do with the endogenous investment share. Okay, so this model is basically looking at the human capital model and asking some key questions, right? So when we defined the human capital model, we had a very specific way we defined S, right, which is the savings rate. And so the savings rate is the same, we said, based between what's it called? Between physical capital and human capital, right? But let's say we we turned the savings rate instead of being entirely exogenous and turned it endogenous, right? Something that's defined within the model. So let's try to work on that and see what we get. So this is what the model says for this question. We have defined S as SH minus SL, 1 plus KT plus SL. Okay. We defined the model as such. Now, whenever we're working with the human capital model, I'm just going to say this up front. It is very important to have a certain equation memorized, right? Of course, given that the human capital model we have the same assumptions of the human capital model otherwise, right? So what does that mean? Basically, the problem says we have all the same assumptions and none of the other things, like, for example, the production function has changed. This is a good thing to memorize. And that is this equation. Okay, why is this important? Because as you're working through the human capital model, and just all of our other models in general, what we really want are things in terms of capital per capita, right? And so if you use this equation, you can convert all your H's into capital, right? And so from there you can go from capital per capita. Makes it a lot easier on yourself and on us. So definitely want to have this one memorized if you can. And again, of course, this only works if the model is the same for example, the growth rate, right? And I'm going to presume that you have an understanding of how this was derived. I could go through and derive the entire human capital model. That would take time. And really, I just want to get to the meat of this question. And so for now, I'm going to presume that you have an understanding of how this was derived, and I'll go on from there. Okay. So now we have this endogenously defined savings rate, right? The question is, does this change our human capital model? Does it change the human capital model, or does it look the same, right? Let's see what happens as we run through this question. So first off, the question asks, a well-labeled figure, plot the function SKT, explain in words what happens to the investment share as physical capital per person increases from 0 to infinity. Okay, so from 0 to infinity. When you hear from 0 to infinity, what comes up in your head? First thing that comes up in my head, limits, right? Remember limits from calculus? Basically, the idea is where what happens as a certain variable increases to infinity. And we look in this equation, we have a kind of a decent idea of what's going to happen. So first off, we notice that KT is in the denominator, right? Capital per capita is in the denominator. Why is that important? Well, if KT goes to infinity, well, we know by properties of limits that this portion is going to keep on going lower, 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 and lower. Because remember, SH and SL are both constants, right? They're not changing, so they're not increasing. But KT continues to increase. So if the denominator continues to go up, that means this thing is going to 0. So that means as KT goes to infinity, the limit of SKT, this first part is just going to 0. Now all we're left with is SL. Okay, so we see that as KT is going to infinity, we're going to SL. Okay, what happens when we're going to 0? What happens when we first start accumulating capital? Okay, we can just plug 0 in for KT to see what that does. Okay, let's just simplify that. That's just because the denominator is just equal to 1. And we can cross these terms out. So now we just have SH. So what does that mean? That means that initially, right, when KT is equal to 0, this is KT and this is our function, 0, that we will hit a point here, right, which is going to be SH, right, because that's what we have when KT is equal to 0. And then, based upon our function here, this is going to keep on bringing it down, bringing it down, bringing it down until all the way until it hits a certain limit at SL. It should keep getting closer and closer and closer, but not quite hit it. As it goes to infinity, it goes to that point. Okay, what's the first bit? What's up next? For question B, we're going to derive the fundamental equation of the human capital model in growth rate form. And so that is find the equation for delta capital per capita T plus 1 divided by KT as a function of KT. And so we're also going to define A as we did earlier in the typical human capital model. This makes it a lot easier on us because, again, that means we can utilize some of these equations from the human capital model. So another thing I'm going to presume that you have an understanding of as we use some of the variables, rather some of the bits of the human capital model is, I presume that you understand how this piece right here is derived. It basically just involved combining like terms once we implemented our equation here, this 1 over A minus 1, KT. Basically, it just gives you this. Again, we could go through the entire human capital model and rederive this point, but because it's so ingrained in the human capital model and very important, because we didn't change the production function, we didn't change anything else about it, we've only changed one exogenous variable, one thing that's not defined by the model, right? We're allowed to just utilize the exact same derivations here, right? So presume that you have an understanding of how it's derived. If you have a question about how it's derived, definitely check out the handouts and read on the human capital model. It goes into more detail there. But we're going to presume that we already know this fact because everything would be the exact same. And notice here, right, in the original human capital model, right, S is determined exogenously. It's determined outside of the model, right? But now we have S being defined endogenously. So let's just replace this S with our S. Okay, so why were we allowed to do that? Well, first, remember, the question explicitly gives us the point that we have everything else from the human capital model. Everything else is the exact same. The only thing that has changed is just one exogenous variable, right? The human capital model has nothing to say about S, right? It has nothing to say about S because S is being determined outside of the model in the original human capital model, right? So it really can't say nothing about S because it doesn't know anything about S. It's just a variable. That means all of our derivations up to this point is going to be the exact same because, again, we just assumed S was something, right? Now we've given definition to that S. So now we can just replace that S here. Okay. Bottom line, though, you could have very well have started off with the human capital model and rederived it based with just replacing every S with this. But for the sake of your time, I won't go through that. Okay, so now we get to the meat of this part. So we want to make this in growth rate form as we typically do. So we're going to divide both sides by nt plus 1. Very important that we do nt plus 1 as opposed to nt, because it wouldn't make sense to have a capital per capita in the future if we compare it with amount of people in the past, right? So we definitely has to be nt plus 1. Okay, and we still know the formula for that. That is just 1 plus n, nt, perfect, plus 1 minus d, k, big kt, and then we have 1 plus n, big nt. Okay, I've already kind of started the process, but as you can see, there are some nice like terms, rather nice things that we've already know the equation for that we can simplify this into. So first, this is now capital per capita. Okay. And so from here, what we're going to do, we're going to find these. And so now we just have this. S, K, T, A, capital per capita, 1 plus n, plus 1 minus d, 1 plus n, capital per capita. Sweet. So now we have things in per capita terms. This is great, but the question's asking us, what is this in terms of in terms of the growth rate, right? In growth rate form. So how do we do that? Well, the formula for the growth rate form is just delta capital per capita plus 1 divided by capital per capita times t. So what does that mean? Well, this is just equal to kt plus 1 minus kt divided by kt. Well, hey, we already have the formula for kt plus 1, so let's just put that in there. So we're going to put this right here. So now we have SKT, right? And then we have KT. This is all over 1 plus n plus 1 minus d, 1 plus n, kt. Okay, and so now we put that in there. So now we're going to subtract kt that we have right here. We're going to multiply that all by kt. Right, so this is all equal to that. So luckily for us, this is very, very easy to simplify because we can just take out all these kts. Now we just have skt, a, 1 plus n plus 1 minus d, 1 plus n minus 1. Okay. Now, technically this is true, right? But let's make it look a little bit better. So 1 is just the same thing as 1 plus n divided by 1 plus n. We really want to have everything having the same denominator. So this is also equal to SKT A plus 1 minus d plus, rather minus 1 plus n all over 1 plus n. We can simplify this, right? So we can distribute this negative to both the 1 and the n. So now we have SKT A plus 1 minus d minus 1 minus n. Okay, and so these ones cancel. And so now we have SKT A minus n plus d, all divided by 1 plus n. Okay, well, this is great. So now we have it in growth rate form. Okay. Okay. So what's next? So we've derived the fundamental equation of the human capital in growth rate form. Okay, and so now we're going to talk about C. Under what conditions does this model have a positive steady state level of physical capital per person, important, and no long run growth? In this case, draw the phase diagram of the human capital model in growth rate form. What's the steady state level of physical capital per person in terms of the model parameters? Okay, so there's two ways of going about this, right? We could just go back up here, right? And we could just rederive, rather, we could just derive the, we could just derive, box is not important. We could just derive the steady state from here, right? Just like we do typically, we can subtract KT and then solve for 0, and we can find K star, right? From here, and then we can kind of plug everything in there. But another kind of important thing this question is kind of giving you, and it's an important thing to kind of think about in terms of a growth rate, is that the steady state level physical capital has no long run growth, right? So what does that mean for us? Well, if it has no long run growth, that means this growth equation right here should just be equal to 0, right? Which is the same thing as the steady state, right? And so let's kind of showcase the importance of that, right? Because remember, the steady state is the point where KT is going to remain forever, right? So if KT is not changing, right, it's not growing. So it's not growing, but steady state. Okay, so let's just say this right there, because the question is asking for us to figure out something if it's not growing, right? If there's no longer growth, it's equal to 0. And again, if this aspect is a little confusing, you could just start from here, then go and figure out what the steady state is. But ultimately, right, remember the formula for delta KT plus 1 is just KT plus 1 minus KT divided by KT, right? And if you were looking for the steady state, right, you would just be doing this, equal to 0. Well, I could just divide both sides by KT, and that's the same thing as KT plus 1 minus KT divided by KT is equal to 0. Right, so you could just do this. And so as you can see, it's the exact same thing. So find the steady state normally, it's the exact same thing as finding the steady state for this, if you make it equal to 0, the growth rate equal to 0. But just want to show you guys that you could do either way. Okay, so let's continue from here. So first step, definitely want to multiply both sides by 1 plus n. So we have SKT A minus n plus d equals 0. Okay. Now what? So typically this is where, we may have an issue because there will be no steady state if you think in terms of like original human capital model, because this S rate was defined exogenously, right? Just provided completely exogenously. And if we presumed that SA was greater than n plus d, then it'd be positive slope, negative, positive, and it's growing. Otherwise, it's something different. Here's the thing. In this one, we actually have KT still in the equation, right? KT is still here because it's being defined endogenously. Okay, let's figure out what that KT is. So we have SKT. We have to go all the way back to our original equation. I'm going to copy this. Okay, we have this equation, right? Let's just plug this in for KT, because at this point, we actually do need to use this KT right here. So SH minus SL, 1 plus KT plus SL, right? That's the entirety of this bit right here, times L minus N plus D. All right, what do we do next? So from here, what we're going to do is we are going to solve for KT, right? So this is still equal to 0. All right, so now we're going to add N plus D on both sides. if we want to divide A on both sides. Oops. Perfect. And now what we're going to do here is we can just subtract SL on both sides. Okay. Now we're going to multiply 1 plus KT on both sides. Okay. Let's just divide both sides by n plus d divided by a SL. Right, so that's just SH minus SL n plus d over a minus SL to 1 plus KT. Okay, so now let's subtract 1 on both sides. Okay, so technically this is true, but doesn't really help us much in terms of understanding the economics. So let's try to make this denominator the same as the other denominator. So we're going to just change this 1 for nd plus n plus d divided by a minus SL. So this is the same thing as n plus d divided by a minus SL. Right. Right. Okay. So what are we going to do next? Okay. So an interesting tidbit here, and oh, don't want to forget, gotta do that, right? Because technically it's also being surrounded. That's negative. Okay. Now from here, what we're going to do is we're going to distribute that across. SH minus SL. Then we have minus SD over A plus SL. All right. Okay. So we can just combine like terms. Right. And so now we just have this SH minus N plus D over A N plus D minus SL over A. Okay. So again, we can simplify this further because look, we have an A, we have a fraction in the denominator. We can just put whatever's in the denominator of the denominator onto the top. And so now we have ASH minus. We're multiplying this A times this and the A times that. So that's going to get rid of the A and the N plus D. And we have N plus D minus SL. Oh, and I just noticed, okay, so actually, this is just only on this term. So that's going to change things a little bit. So from here, what we're doing, so erase this actually. Okay, and so from here, we're still crossing out our SH, rather, we're still crossing out our SLs, right? And so now we have n plus d for a minus SL. Okay. So now what we can do instead is we can actually make this a little simpler on ourselves. We really don't want fractions and everything. What we can do is multiply a times a on both top and bottom, because that's the same thing as just one, right? Okay. So from here, what we're going to do, so we have a sh minus a times n plus d over a, n plus d divided by a times a minus ASL. Okay. And from here, this just makes it ASH n plus d divided by, these cancel, so we have n plus d minus ASL. Okay. So why do we go through all that, right? So at this point, we found the growth rate. We found the steady state, right? And so the steady state here is important because, as I mentioned earlier, the steady state is also the point where the growth rate is going to be zero, right? Because it's not growing anymore, it's not changing. Okay. And so the question says, draw a phase dot under what conditions does the model have a positive steady state and a level of physical capital per person and no longer in growth? Okay. So looking at this, right, we need to be positive, right? What would make this positive? Well, first off, right, we can just do ASH plus D, N plus D, ASL. If we want this to be greater than zero, right, what we can do is we can just see what condition we need, multiply both. And this is, by the way, this is encapsulated negative, right? This is not like a single negative on that, right? Okay. And so what we can do here is we can just multiply n plus d minus ASL on both sides. And then we have a sh minus n plus d greater than zero. Now ASH greater than n plus d. So we know this is one fact we have to have. Right? So if this part is true, then we're in good shape. That's the first part we need to be true. Another important factor is, right, looking at this model, right? We also need the bottom part to be positive too, right? So if the top part is going to be positive, the bottom part has to be positive too. Why? Because if the bottom part is negative, then we have a positive being divided by a negative, and then we have another problem, right? So this is one of our conditions. We need one more. Other condition can be found here on the denominator. So what would make this denominator positive? Let's check. What would make this positive? Greater than zero. Add AS on both sides. N plus D is greater than ASL. Okay. This is our second assumption that we need to be true. So it needs to be the case that ASH is greater than N plus D, and N plus D is greater than ASL. Okay. And so why is that important? Because we want this to be positive and basically be defined as the things in the problem. Okay. So now we can actually finally start drawing our graph. So if we remember our growth rate model, our growth rate equation, a little bit of ways away, but we'll get it right here. I'm going to copy this. Right. This, and so let's draw our our growth rate. So what happens to that over time? T plus 1, right? And so we know that we're going to hit 0, right? Because we already stated, like, what's the growth rate going to be at, we figured out what the steady state is going to be at that certain time, right? So if we plot it out like this, we know we're going to hit 0 at some point, and we know that some point is going to be at k star. That's the first thing we know, right? Now, how does this function look? Let's write down our equation as, oh, brother, this is the equation right here. So it's SKT A minus n plus d divided by 1 plus n, right? And so remember, we saw what happens to SKT as it increases over time, right? It goes down. Just like we did all the way at the very beginning of the problem, it just slides down, right? So that means we can take that into account. Okay. So do you remember how when we were first doing this, right? We were asking, okay, where does SKT go at 0 and where does it go all the way to infinity? Now it becomes important because now what we can do is we can figure out exactly what this line is and where it starts, right? Because our formula is just SKT A minus n plus d divided by n plus n, 1 plus n. We can substitute this at time 0 for what? Well, we know this is SH at time 0, so we can just have it like this. This is just a number, so we know it starts at that point here. So SH A minus n plus d by 1 plus n, right? Okay, so it starts there, and then it's going to go down, just like our normal function said it would, right? It's going to go down. Where's it going to go down to? Rather, oops, let me just make it look somewhat comfortable. I'm going to redraw where I put my steady state. We're going to bring it down, and then okay. So this steady state is our k star that we talked about earlier. And so where's it going to go to? Remember, over time, right? Where's this going? Where's it going to as it goes to infinity? Remember, we figured that out. It's just going to go to SL, right? So it's SL A minus n plus d over 1 plus n down here. This is our formula right here. And this, it's just that. Okay. Now we have a model showing what happens to the growth rate over time. And we figured out what a steady state is if we have these assumptions, right? And so D is asking a slightly different question. Under what conditions does this model predict endogenous long-run growth, right? What does that mean? That means we don't have a steady state, right? That means we do not hit that 0 point. If we hit 0, then we have a problem. Because if we hit 0, that means we're going to stop growing capital, which means we're going to stop growing. So what we're going to do, well, let's figure out under what conditions the model will predict endogenous growth. So let's go back to our original equation here, right? We have a steady state here, right? And that's all well and good. But what we can do is we can actually check out our graph here to kind of get a better insight of what we want to do. So notice, it's going down and down and down until it reaches SLA minus N plus D, right? What if this just never reached zero? Right? What if this value right here hung above zero? If that hung above zero, that means it would never hit zero. That means it would never hit the zero line, which means it would keep on growing forever, right? So what would it take for that to be greater than zero? Let's check that out. So if SL A N plus D 1 plus N was greater than zero, what would happen? Or what would we need to be true? Well, okay, we multiply both sides with 1 plus N, SLA N plus D. Right, so now what we're going to do, we're going to add N plus D to both sides. And look at that. We need this to be true. If we have the condition that SLA is greater than N plus D, we then know that the model will predict endogenous long-run growth, right? Why? Let's draw the model again. Here it was SH A minus. Right? That's the first part. And then we are going down to that point. This is zero. This is zero long-run growth. Oh no, right? So it never touches zero. This is our formula right there. Let me write that down. P2. This is the change. Growth rate, rather. Okay. I'll rewrite the equation. S of KT A as N plus D 1 over N. Okay. Notice we never hit zero. We never hit zero. We never hit steady state. So bottom line, right? We also see this further if we look in our equation here. If this bottom piece right here is greater than this, that means this is going negative and we have a problem. And so because of that, because we broke that assumption, now it's just sliding on top of zero, right? Remember, the key thing to remember is in growth rate form, if we hit zero, that means we have a steady state. That means we do not have long-run growth. In this case, we do have long-run growth because it never hits zero. Okay. So, so now going to D, right? And so it never converges to a, it's important to note, like when I say steady state, right, I'm talking about it doesn't go to a steady state for rather we never had a steady state for just in terms of per capita terms. The growth rate, right, we're converging to this point right here, right, where this line is just like last time it was SH A minus N plus D. It's a little confusing, but basically there's a difference between hitting zero, right, converging at zero, and then also converging here. Okay. Right. So then then the question asks us to do one other thing. It asks us to see what would happen. What is the steady growth rate of output per person, right? So, okay. this is associated with the growth rate, right? And so how do we do that, right? How do we determine, say, how do we determine the growth rate of output per person? We typically do it in capital per person. Well, same deal. That's the equation for delta YT divided by YT, right? Plus one further. Okay. So let's figure out what. So what is YT, right? What is output per capita? Well, let's write down our equation for Y. Right, by NT. So we have going all the way back to our equation for the human capital model. It is B K T A H T 1 minus A. We're going to divide that all by NT. Right? So what do we do next? And so from here, what we're going to start trying to do is utilize our equation that we talked about at the very beginning, right? Very beginning of this problem, we talked about a certain connection between H and K. Let's just copy that down. So we're going to use it here because it's a lot easier for us to then swipe our swap our now in capital terms. Our H for paste this right here. H for this. Okay. Okay, and so from here, what we're going to do is we're going to have B, KTA. This is the same thing as KT minus A, 1 minus A minus 1, by T. So from here, this is from algebra, we can just combine our exponents. And so now we have KT1 over NT. That looks familiar to us. Let's say. So from there, that is the growth rate form. Rather, that is the per capita terms of capital. Okay, so wait a minute, does this look familiar to us? It's close, but it's not quite. Basically, do you remember our formula for A that we used in the human capital model? So in the human capital model, we have the formula. A is equal to A 1 over A minus 1 minus A B, right? Okay. And so from here, what we're going to do, so this looks very, very close, right? This part right here looks so close. Only difference we've just, we don't have the A, right? So if we divide both sides by A, then we have the exact same thing, right? And so that means we know that YT is just equal to A divided by alpha, right, KT. So what was the point of doing all of that? Well, now we know what YT is in terms of KT. So now we can actually figure out the growth rate of KT. And in fact, it's going to be something kind of interesting. So if you look at the growth rate of YT plus 1, that's just equal to YT plus 1 minus KT divided by KT. Rather, YT okay. And so we can just replace our YTs with this. Okay, and then we have KT plus 1, other KT. Okay, so let's notice something we can do here, right? So this 100% is the growth rate of plus 1 divided by YT. This is this equation. What we can do is we can actually multiply this by A divided by A, divided by A, divided by A. Right? This is just 1, right? So we can do this. This is legal. And so from here, we do this. Oh, my apologies. This is just KT. There you go. And so now, right, what we can do is we just multiply this out across both. And now that just turns into KT plus 1, right? And so because those cross out, then multiply on the bottom, that also crosses out. So we have KT plus 1 minus KT over KT. Wait a minute. This is just our formula for delta KT plus 1 divided by divided by KT. So turns out this is equal to this. Okay, well, if that's the case, then we already found the growth rate of steady state growth rate of output per person. It's the same thing as it was up here. Right. And so if we want to continue along these lines, right? Remember in our equation for this one, for F4, we see that's going to this for KT. That means it's also going to go to that for YT. So that means the steady state in terms of growth rate, very important for growth rate, is just this. The growth rate for YT. Oh, oops. Oh, I think, oh, yeah, I took the, I put the wrong deal here. This is, that's a yes, L. Yeah, this is going to L as opposed to H. There you go, so this is just SL. Okay. And so from here, we have that the change in YT is just this. Okay. So now the final question we want to consider is, does this model predict conditional convergence, right? And so the key idea here with, whenever you think about convergence, right, the key idea we're trying to think about is, when you have high amounts of capital, are you growing slower? And when you have low amounts of capital, are you growing faster, right? So look at this. Look at our model here. A low amount of capital, high growth, right? Because we have a very high value for our growth rate. We have a lot of capital, low, right? Lower growth. So it's growing faster when we have more capital. It's growing faster when we have less capital, growing slower when we have more. Same thing with this one. High, low, right? Same deal. Okay. And so you also go into this more mathematically involving derivatives, but frankly, the model, the visual, I think really, really helps. Looking at this and say, okay, if I increase my amount of capital, do I get more growth or do I get less growth, right? My growth going to increase or decrease? And so we see here that, yes, the model showcases the fact that there is an inverse property where if you have high amounts of growth, rather high amounts of capital, you have a slower growth rate. And if you have less capital, you have a larger one. Okay, and that does for the problem. Thanks so much for watching.